All right, here we go. Let's take a look at the AP Precalc exam here. We know we got multiple choice and free response, and you can see the percent each section's worth. This unit is going to be all about getting you ready for the FRQs, man. So part A is going to be with the calculator. You got 2 questions on the calculator. Then part B, no calculator. You also have 2 questions. About 15 minutes per question to make sure you're good to go. Awesome. So what's nice about the FRQs is we know what to expect. They're not going to surprise you with anything. We know what's coming. So we can really get ready for this. We don't know what the problem's going to look like, but all they're going to do is change the numbers and the equations and things like that. So FRQ1, let's lock in on this bad boy. We know it's calculator active. There's no context, so no word problems or anything like that. It's only over units 1 and 2, so like, you know, our polynomials, rational expression or functions, exponentials, logs, those type of things. And it's going to be a table or a graph given to you. Here's some extra topics that they're going to always have on there. And let's dive into it, man. I think the best way to do it is just get in there. Okay, so don't freak out. Sometimes these things can look a little bit overwhelming when you first start, but they're going to give you a function. Now, in this case, this is the one where they give you the table. They're going to give you the f of x as a table. Awesome. Then they're going to give you another one. They're going to give you g. G of x is the equation here. So we have 2 different things going on, but one of them will always be an algebraic, some kind of equation down there. Excellent. So let's see if we can use that information to answer this bad boy. So part A is about composition of functions. They won't write composition of functions on there. They'll just say part A. But I just wanted to make sure you knew what we're getting into here. So what is a composition of function? Well, I'm going to build h of x using the g of f of x. Or some people like to write it like this. They're both the same thing here, the g of f of x. So this is pretty chill. You want to find the h of 3. Boom. We're just going to throw it in there. We're just going to say, hey, what is the h of 3? And so pick the notation you prefer. I'm kind of more on this team over here. I like to say the g of f of x. What is x? X is 3. So I'm going to put it in like that. Boom. There it is. So I'm just plugging in the notation. Then what's the f of 3? We'll go to your table. I know when x is 3, it produces 17. So you're really saying, hey, what is the g of 17? So it's really just a lot of plug and chug. Fantastic. So now I'm going to put this into the g equation up here. You don't even have to show work. I'm going to go straight to Desmos. You can go straight to your Desmos, or you can watch my Desmos, somebody's Desmos. I front-loaded it for you here. Here's the equation. You can see the picture over here. But I really want to know, I really want to evaluate this function. So I'm going to say, hey, what's the g of 17? Thank you, Desmos. Hooks me up there, 1.125. So we can come back to this, and we can say the g of 17 is 1.125. So as long as you're showing your notation, you can say you got the f of 3 from the table is cool. Or you can actually show you're plugging in here. If you really want to show all that, you can plug in, hey, what is the g of 17? We're just evaluating it here. Boom, there's some work there. But that's all we need there for the answer. Fantastic. All right, how about the second part of A? So this, if you had a table, you're going to usually do something with inverses. So let's talk about inverse functions real quick, make sure we're cool. So remember, I like to say, okay, if I've got a, whoa, that's a crazy f. Let me try that again. I got a function f. Then I've got his inverse over here, whoosh, f negative 1. So I like to think, what happens here? Remember, you switch the point. So like, if I'm looking at a point, we're saying, what is the inverse here? So we're going to say, hey, when I put 2 into my inverse, what comes out? So that's what we're saying here. So what does that mean in my regular function? You switch them. I'm going to say, hey, what x makes that y? So here, 2 makes something, something makes 2. They're always opposite. So you can kind of, that's how I always think about inverses. You're switching x and y. So if I look up at my function, what makes 2? Boom, there. Let me use a different color here. There it is right there. What makes 2? 0 makes 2. So if 0 makes 2 in my function, I'll write it down below so you can see it. If 0 makes 2 in the function, what happens here? 2 makes 0 in the inverse. We're just switching x and y. So we can say the f of the inverse of 2 is 0. So just use that table. Awesome. Part A, done. Let's look at part B. So I kind of highlighted because of the, so we can see it, the key parts, the table and the graph, I'm sorry, the function, g, f, and g. Now let's get into it. Make sure you know what you're looking for. So I'm looking for the g of 4. So I want to find all the values when the g of x equals 4. So again, I'm going to go back to Desmos here and see if I can solve that. So what am I going to do here? A couple options. I'm going to say, hey, let's just graph 4. and see what we get. There's a line right there, and boom, when does it equal 4? 5.5. So that's how I like to do it. You can just say, when does this function up here equal 4? So we got 5.5. So luckily we haven't had to, ooh, what's going on there? Luckily we haven't had to round too much. It's always 3 decimals when you're doing your rounding. But from Desmos, I'm going to say, hey, when x is 5.5. Boom. So if you want to say you graphed it, if you want to set up your equation, you're really looking for, the key here is you make sure you know this is what you're looking for. In this case, we actually could have just solved it, couldn't we? So this one's not too bad. Sometimes we don't want to solve it, but you could have solved that. But it happens when x is 5.5. Excellent. Then just make sure, again, we're going to hit that in behavior. Make sure you know what function you're talking about. We're talking that g functions, and we're increasing without bound. So they want the correct notation. You must use the correct notation on this. So you must write it exactly like this. You must say, hey, the limit as x increases without bound, so as x goes to infinity, of what? Make sure you're saying the g of x. Make sure you, not f of x, is this g of x. And what's going on as it goes to infinity? So you can think about the graph, what does the graph look like? But because I've got Desmos and I'm calculator active and I got it in there, I can just look over here. What happens as this goes forever and ever and ever? What's happening in my in behavior? Yeah, I can see it's getting lower and lower. It's approaching 0. And that makes sense for all our rules. Let's go back to this. First, let's make sure we get the right answer. We're going to say it approaches 0. Gets smaller, smaller, smaller. And that makes sense because the power on bottom is bigger. It forces that to 0. So make sure you have proper notation here, and then you'll get all points. Nice. All right, the last part. Dude, we're cruising. Last part here. Now we're going to do some kind of justification. When we got a table, so they're going to have us look at the table. So we're back to F. Keep switching around. What model is this? Are we going to do a linear, quadratic, exponential, or logarithmic? So as you look at this data, we got to say, well, what is it? So I think I have a little chart I made here. If I can grab it. Oh, come on up here. There it is. This will help us decide. So this should help us decide. If it's linear, we're looking for constant rate of change. Quadratic second difference is a constant rate of change. Exponential, we are always timesing. And then I think of logarithmic as the opposite of exponential. So your x's are timesing, not your y's. That's kind of a weird one. We'll do them though. All right, so here's the key. These are always counted by the same thing. I'm counting by ones. That's great. And then what's the pattern here? Going on and on. I don't see much of a pattern. I'm not doubling, but this went from 1. This difference is 3. This is 5. Oh, there it is. And then what happens here, when I see that pattern, I know it's going to be quadratic because whoosh, we've got this second difference of 2. So in this case, this one we decided is going to be quadratic. Awesome. So you get a point just for naming it. Good job. That's cool. Hook it up. Now, how do we justify that? So part 2 is going to say, well, tell me how the table tells you why'd you pick quadratic. So name it. Now, what I did for you here, and I hope it hooks you up there a little bit, is I made these things, these little sentence frames for you. You don't have to use these, but I just thought if it helps you, great. You do have to say something about the second difference is a constant rate of change. That's the key thing I'm looking for here. So if you want, this little sentence frame works for anything. You just fill in the values for your problem, and then that'll get you full credit for the FRQ. Okay, there is the model response right here where I said first difference output from the table up here are 1, 3, 5, 7. The second differences are a constant at 2. Because the second differences are constant for equal changes of the input, don't forget to reference that these have to be equal up top as well. Then the function is quadratic. So again, I snuck these sentence frames before your practice, right after your notes, so you can have them for examples when you're writing up your perfect responses too. Boom, there it is. We just crushed our first FRQ. Fantastic. Let's take a look now at the next one, but what if I give you a graph instead of a table? So again, the same thing's going on here. Let me get my fancy highlighter. And I'm going to say, hey, this is the graph of F. Make sure you know that's F. Down here, here's G. G's an equation. So they're doing the same thing. I want you to go ahead, just pause it and try it. See how far you get, and then I'll highlight some important things here. But it's very, very similar. Give it a shot. See how you do. Good luck. All right, here we go. Let's take a look, and I broke them down into each part. So here is part A, so we can zoom in. I left the graph up here, we can see it. So again, we're doing composition of functions. Hey, we're actually plugging 3 in again. That's cool. The f of 3, now instead of using a table, you use the picture. Plug the old 2 in. Plug that bad boy into your Desmos. Oh, I showed my Desmos up there. It makes negative 7.2. Awesome. How about part 2? So from the graph, they want to know find all values x where the f of x equals 1. So remember, you're kind of doing it backwards this time. So I want to know what y value has 1. So you're looking at this line right here. Where does it touch? It looks like it touches a couple different places. It's going to be -3 and 2. So hopefully you see those points. At -3 it touches, and at 2. Awesome. So it's just backwards. Fantastic. So using the picture. Great. How about the next part here? So again, I kind of kept our g of x and f of x so you can see them. I put the Desmos over here of just the g of x. Remember, that's your g of x. And then let's go ahead and what's going on here? We're going to do the same thing. When does it equal -1? So I graphed it right here. Again, here's the difference. It was actually 1.358 something. I can't even read it. 5. I like to truncate. This is me right here. I just do 3 decimals and stop writing. I'm just done. I don't even look at what's after it. But if you really want to round it, you can. Either answer is fine. Both are acceptable. But I think 3, I don't have to think anymore. Just do 3 and you're done. Awesome. Make sure you have the correct notation again. We're still increasing with bound. It could decrease without bound, so you could go to a negative infinity. In this graph, as it goes on forever, where is it going? It goes down to negative infinity forever. Awesome. Hopefully you're crushing it. Part C. So again, there's the prompts up top. Now we're doing our inverses. Inverse is going to be snuck in there somewhere. So does it have an inverse? Let's get that line going again here. I said no. No inverse. And what's the short answer? Well, the short answer is the vertical line test. Do you remember that vertical line test? Let's go down and look at it right here. So here's the formal answer. So I did the nice formal mathematical write-up. But basically, you have to pass the horizontal line test. So if you pass the horizontal line test, then your function will pass the vertical line test. So in this first picture, it's supposed to be a straight, flat, nice flat line right there. So as I take this and I scroll down, see how it only touches one time? It's only touching once. If you can do that, you're a one-to-one function. That means you have an inverse. Every input makes one output. That's what I always like to say. Every input makes one output. But if I've got this over here, it's not one-to-one. Why? Oh, man, because boom, boom, boom. See how it's hitting these different places? You can't do it. So if the function doesn't pass the horizontal line test, then its inverse will not pass the vertical line test. But here's the formal one. It's not one-to-one because there are 3 different inputs, and I listed them, that make the same output value of 2. So what happens on our bad boy up here? Is that going to pass the horizontal line test? It's not. Spoiler alert, it's not going to do it. So pick a point. You can actually pick the one from what we did earlier, didn't we? Didn't we just do one where it hit twice? I think this was from the last thing. So right here, there's all kinds of examples. Any line up here hits 3 times. So let's write that up so we've got that nice formal answer. Okay, there's the nice wrap-up. I'm sorry, write-up for the example we had here. The function f is not one-to-one. Why? There are 2 different inputs. -3 and 2 that produce the same output value of not 2, Mr. Bruss, that's a rookie, of 1. Let's change that real quick. But you can see it makes it here and here, not one-to-one. You could have picked anything up there. That's just the ones I picked. So another way to remember it is they're always, one-to-one functions are always decreasing or always increasing. They can't have any little bumps in the road. So if it's not one-to-one, there is no inverse. Rock and roll, that's it. Go ahead and do the practice. They're out of 6 points total, and I put scoring rubric style grading on there, so I want you to do them, grade them. Tell me how many points out of 6 you got. Do your best with that. Good luck.